Science is for everyone. Science is for everyone. Science is for everyone. C2ST. 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 Chicago Council on Science and Technology. C2ST. 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 Chicago Council on Science and Technology. Science is for everyone. Science is for everyone. Science is for everyone. C2ST. 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 Chicago Council on Science and Technology. C2ST. 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 Chicago Council on Science and Technology.
Hello, everyone. Thank you so much for joining us tonight. My name is Denise Hernandez, and I'm the program manager with the Chicago Council on Science and Tech, or C2ST. Welcome to tonight's program, all about quantum information science computing. This program is presented to you by the Chicago Council on Science and Tech. If you're new to our organization, our mission is to inspire and engage all segments of society about science and tech and their contributions to society. We're so delighted to be entering our 15th year of offering science and tech programs such as this one to the public. To ask questions, please visit c2st.cnf.io for answers after the presentation, and visit c2st.org to learn more about upcoming programs and to donate. Our staff will also be checking C2ST TV, YouTube Live, and Facebook Live for your questions. Again, to ask questions directly, please go to c2st.cnf.io. Once again, to ask questions directly, you'll go to c2st.cnf.io. I have the immense pleasure of introducing Sarah Sussman, today's amazing speaker. Very briefly, you can learn more about them at c2st.org or c2st.cnf.io. Sarah Sussman is a fifth-year PhD student and an NDSEG fellow at Princeton University, working in Andrew Huck's Superconducting Qubit Laboratory. She is an incoming Letterman postdoctoral fellow at Fermilab starting in the fall of 2023. Sarah also works on engineering superconducting qubit systems, their design, fabrication, and control. She is also a member of the Quick Open Source Qubit Control Project. Please join me in welcoming our amazing speaker, Sarah Sussman. Sarah, I will hand it off to you.
Hello, everybody. Thanks for having me. So hopefully soon my slides will be on the screen. Okay, great. Okay, hi everyone. Reporting to you from Princeton, New Jersey. I'm just a grad student and I started learning about qubits and quantum computing a couple years ago. And today I'm just going to try to tell you what I know. First of all, what is quantum computing? So this is a device which I was working on yesterday, so it's not quite done with some other students, but this is a device with 2 qubits which can be entangled with each other. So I just thought I'd show this up on the title. First, we'll talk about classical bits. So a classical bit is either 1 or 0. And you might look at these two strings of bits on the screen and you might not know what they are. And it turns out that they could be many things, and classical bits could be used to express anything. So, for example, the top row in decimal, if you convert, it's this big number, and the bottom row, if you convert to ASCII, which is what text letters are, it's the word sun. So you would have never known that, but everything can be described with classical bits. This is a little bit of a complicated example of classical bits. Here, this is a cool example of how classical bits can be used to program a whole chip, like your cell phone chip. So basically, what happens is these bits go into the chip, and then they actually end up creating pathways through the chip based on parts of the chip being on or off. So this is from a cool tutorial about how to learn how to program chips. So I recommend it if you want to learn. So what's this big thing in the middle? It's what's called a logic gate, and it sets the rules that the bits are going to follow as they go through the chip. So actually, this all was only invented less than 100 years ago. So basically, Claude Shannon said that you could make circuits using bits, and you could simplify those using these logic gates. So this is an example of a circuit where bits can flow through. And this circuit allows you to switch whether this input 0 or input 1 gets passed through to the end, which is called Q. Because depending on what A is, it's going to let either one input or the other in. And that's all determined by how the bits are moving. So depending on what the bits are here, the output at Q is going to be different, and it's all going to follow this one rule. And that's called the truth table. So you might notice that actually all these gates are the same. They all look the same with the same symbol. And they're called NAND. So without explaining what that is, I'll just say that you can write every gate in terms of NANDs, for example. But in real life, we actually don't use the NAND in a cell phone chip. We use other gates, which are more efficient based on how much power they take up and how easy they are to make in a real chip hardware. So keeping going with classical bits, you could design a chip which uses classical bits. And first, what you'd want to do is decide you want to make a design. You would describe what you wanted to do, and then you would decide what your circuit on your chip would look like in terms of those gates. And then you would try it out and then see how efficient it was. There's many ways which the chip could be more or less efficient. It might take many long moments for information to pass through based on how you made your circuits. And actually, there's any number of things which could go wrong or right, and all those things are costs. So when you work with bits, you first make a design, and then later you find out what is the cost. And then you keep trying that again and again. And somebody who's experienced might know how to make those designs while incurring the least cost. And this is a very fun process. Here's a quote. The optimist sees the glass half full, the pessimist sees it half empty, but an engineer sees it twice as large as it needs to be. And that means the engineer wants that glass to be smaller because it wants to have a smaller cost of its design. So making things smaller and more efficient and less costly is the name of the game with classical bits. It's also the reason why your cell phone is so powerful. And now we are going to move on to the main event, which is qubits and a quantum computer. So quantum computers work differently from classical computers. Instead of using bits, quantum computers use quantum bits, which is called qubits for short. Qubits are special quantum objects which, if you engineer them properly, could be used to gain a computing advantage. This is what we're going to be talking about in this hour. Now, before we discuss any specifics of working with the qubits, we need to understand one important thing, which is that the quantum object behaves differently from a classical object. So we have to first talk about quantum objects and what they are. All right. So the first thing that we need to know about quantum object is that a quantum object each has a quantum state. One object will have one state, and the quantum state will obey a rule, which is called the uncertainty principle. Now, let's try to understand the uncertainty principle. A classical object can have a position and a momentum which are independent from each other. This is my favorite soccer player, and you can see that he's kicked the ball, and the ball's position is totally independent of the momentum that it has in its flight. Okay, now a quantum object. The position and momentum, for example, of a quantum object are actually connected to each other. They are connected parts of that quantum state. They're not independent of each other. Okay, now I'll just mention one last thing, which is that you don't know what the answer will be when you're trying to measure a quantum object. You're going to always have some uncertainty, which we're going to call delta x associated with measuring x, and then an uncertainty delta p associated with measuring p. So we're never going to know for sure the exact coordinates x and p. Now, since x and p are connected, if delta x is small, delta p is large. That is the rule of the uncertainty principle. And you might have seen this equation somewhere in your life before, maybe in like a decal or like a button, or somebody has a tattoo of it, or you might have seen this looking thing before. It's kind of famous. So this is the uncertainty principle. Okay, so they're connected, and their uncertainties are connected. And their uncertainty can't be zero in both of them. The uncertainty principle explains the two phenomena that are used to do quantum computing: superposition and entanglement. But one last thing, we need to learn how the quantum measurement actually works. Quantum measurement. So in our example, we were talking about the coordinates x and p of a quantum state, position and momentum. It's your choice. You can either measure x or p. And in this picture, we've chosen to measure x. Our quantum state is this green oval. The uncertainty in x, after we measured it, is very small. You can see that this is very skinny. But because of the uncertainty principle, the uncertainty in p is very large, so it's very tall. The area of the green oval, which is our quantum state, is always a constant because of the uncertainty principle. Now we understand how to do quantum measurement. It's very different than classical measurement. But now we understand what superposition is. Before we do a quantum measurement, the state is actually in a superposition of many values, anywhere inside this green shape of both x and p. After we did the quantum measurement, the state is not in a distribution of x anymore because we measured x. So to an extent, we know what x is, but it is still in a distribution of p. Okay, so that was superposition. Now we'll do entanglement. Entanglement is equivalent to the uncertainty principle, and we're going to explain that. So, this is a picture of a firework. In both classical and quantum physics, momentum is conserved. The firework began with no light, and the object of the firework was in one place in the sky. But then it burst, and all of that explosion fanned out in a perfect sphere. So basically, if you were to sum up all those coordinates, it would just sum back to 0 in the end. That's what conservation of momentum means. Okay, now to entanglement. So we're going to imagine that there's a particle at the source, and it's going to decay into 2 smaller particles. And they are going to fly in opposite directions. That's because momentum is conserved. So that means that if we were to measure x and p at this detector by the conservation of momentum, well, we should measure minus p for the momentum over there, because it began with 0 momentum, and minus p plus p is 0. Also, we know that it's flying in an opposite direction. Okay, so we know what we might expect classically. 2 people, A and B, are on each side of the setup. A will measure the x of one particle, and B will measure the p of the other particle. So that's totally possible. Let's say A measures x. If delta x, the uncertainty in x, is small, because of the uncertainty principle, delta p is large. If B measures p, delta p is now small, and delta x is large. If they measure at the exact same time, how is this possible? It's not possible. Nature does not let you make both measurements accurately because the uncertainty principle applied across the vast distance between the 2 particles, which have flown apart from each other. It's a roll of the dice as to which person's measurement will work each time, and you can't tell which one worked. Both are distributions. What really happened was, since the particles came from the same source, the x of the left particle and the p of the right particle are not independent of each other. The 2 particles are entangled. If both people measured x, they could get consistent results every time, and the measurement would not be a distribution. So that is a complete outcome of the uncertainty principle. We'll talk more about this. So this was proposed as the paradox by Einstein, Podolsky, and Rosen in 1935, 3 years before the logic gate. The origins of entanglement have been debated ever since. The first experimental evidence for entanglement came in 1949, when this physicist, Chen Wu, devised an experiment which documented the evidence of entanglement. So this is the physicist at her apparatus, and this was her paper. She and her graduate student made an experiment where they had a source of radiation, and the particles flew in opposite directions, and they measured them at the 2 directions, and the evidence suggested that the particles remained polarized relative to each other, as if they were somehow connected at a distance. Later, in 1964, Bell proposed a specific test to tell if this correlation is quantum or if it could somehow be explained by anything else. So that's called a Bell test, and you might have heard of those before. But the problem is that we need to make sure that when we're doing our Bell test, the 2 detectors are measuring in random directions relative to each other. That's because that's the only way to avoid a classically possible distribution. So, in order to tell if the correlation is truly quantum or not, or whether it could have possibly made in any other way. So people went to great lengths to try to do a loophole-free Bell test. Well, how did they do it? Well, the 2 detectors, the axes with which they were measuring, was it x or was it p? Those axes were chosen by completely random methods. For example, from the light of distant quasars, which were so far apart from each other that they never overlapped since the Big Bang. So those two quasars never touched each other and never influenced each other. So they must give totally random instructions relative to each other. Like if one sends a photon, that would never be because of the other one. They were never connected in space and time since the Big Bang. So this won the Nobel Prize in Physics last year, these tests. And they found that you could make a relatively loophole-free Bell test, which shows that some correlations are quantum, the result of entanglement. Now on to qubits. So remember the measurement axes x and p that were connected to each other? For a qubit, we can envision measurements along similar types of axes, the axes of a sphere. So basically, there are 3 axes that a qubit can be measured along. This one's called x, y, and z. So that is just kind of an abstract way of visualizing the qubit. But these are the axes that we are allowed to measure qubits along. We'll talk more in detail about what real qubits look like soon. And this kind of abstract way of looking at the qubit is called the Bloch sphere. So a qubit state is somewhere on the sphere. So we can make a maximally entangled state using just 2 qubits. So the first thing we do is we rotate the state of one of those qubits on its Bloch sphere into a superposition state. So if you look at my mouse, we've rotated it from here to there. That's different from measuring it. You can also control the qubits by pulsing them in order to bring them around the Bloch sphere. So now the qubit is in a coherent superposition on the z-axis. So it's in a distribution of z positions. Now we're going to entangle the top qubit with the bottom qubit. And this is a description of what a quantum logic gate looks like, kind of like the NAND gate that we were seeing before. So now, as a result of this, there's now a 50-50 chance that the 2 qubits quantum state is either 0, 0 or 1, 1. But the qubits are connected to each other always. If you measure one qubit and you find it to be 0, after doing this, you know the other qubit is 0 too. Now to the benefit of using qubits. So this is a matrix which shows the possibilities of where that 2 qubit quantum state could be. Could it be 0, 0? Could it be 0, 1? Could it be 1, 0? Or could it be 1, 1? And we see that it could only either be 0, 0 or 1, 1. So we only had 2 qubits, but we have 4 possible states that it could be found to be measured in. And these kind of possibilities are called amplitudes. And it turns out that if you have 3 qubits, you have 9 amplitudes. And if you have 4 qubits, you have 16 amplitudes. The space of amplitudes is a very large sample space. And algorithms have been designed which make these amplitudes compute. So, in other words, an algorithm is designed to produce a set of amplitudes which does a computation in the end. Even though you can only measure one quantum state at the time. You can measure 1,000 times and then get a distribution of amplitudes. And then you really know a lot of information. So the problem in real life is that qubits could decay before we complete our computation, like that circuit on the last slide. So there's 2 ways that a qubit can decay. One way is the way where it decays along the z-axis. Let's say we moved it to the 1 state, but then it lost some energy somewhere physically on the chip. It lost some energy out of that qubit. And then the state went back to 0, its ground state. Or we might position it on the equator of the Bloch sphere, and then it might decay along to the other side of the equator. And meanwhile, there might be some kind of jitter along that axis too. So these are two kind of physical ways that a qubit can go wrong. Then we have to prepare it all over again, and our computation didn't work right. Now, to do logic with the qubits. We can see overall we've learned a few things, but mostly it's kind of like classical logic. We have some new functionality here, and we also have an added cost. The new functionality is on the lower levels. We can have qubits now, and a large space of amplitudes to sample from in the end. We have logic, which is called entangling gates and qubit rotations. And the exact layout for a qubit chip is something which we are working on figuring out. The layout which incurs the least cost. Our new cost is qubit coherence, which that impacts us on all levels of the stack, going from the bottom to the top. So, working with qubits is exactly the same as working with classical bits. You have to make a design for a qubit chip and then find out what is the cost and keep going from there. Now, let's look at some pictures of prototype quantum computers. So these type of quantum computers, prototypes, is called superconducting qubits. And they live on just a simple planar chip. And this is one on the right, which is made by Google. Actually, that chip has many layers on it, 2 in a stack. So things from the top layer can actually communicate electrically with things on the bottom layer. So these kind of chips are actually easy to fabricate, control, and iterate. You can keep designing them rather rapidly. The fabrication is done by hand, even in the industry, for now. And we're just making these chips. So here are some of my favorite chips. This is a chip made by ETH Zurich in a nice publication from last year. This chip has 17 qubits on it, and you can see that it's rather small. It might be about, maybe 15 millimeters or something like that. It's not very big. And this paper was really wonderful because they used all 17 qubits together to try to make one bigger qubit, which was error corrected, which we can talk about in the questions if people want to learn about that. Most of all, I love this paper because they explained and they showed the exact picture of their chip, and they showed what everything looked like on the chip and where it was placed and spaced so that everyone could learn how to make qubits that look that nice. Now, here's another paper which I really like. This is a paper by Google. They didn't show a photo of their chip, but they showed a cartoon. And their chip has 127 qubits on it. And out of that, they used around 49 of those qubits. And what they did was they used a patch of 49 qubits to try to do error correction. And they found that it was just slightly better than using a patch of 17. So that means that even though those qubits have T1 and T2 decay, and they decohere, even if you used more than twice as many, they perform even better than if you used less. So if more qubits perform better than less qubits, then we're doing something right, and the field is moving in the right direction. It just performed ever so slightly better, but this is still very interesting and a great paper. Okay, so here's the thing which I made for my PhD thesis. So this is kind of what I do as a grad student. So I made this special diagram of all the chapters in the thesis and all the things which I've worked on and learned about during graduate school. So you can see it's a little confusing. So basically, I just wanted to show you guys what this looks like, because there are many projects that you can do in school to learn about qubits and how they work and use them. Here's some devices from my lab. So I work in the Haupt lab at Princeton, and we have several interesting qubit chips. So one chip that we work on is a 2-qubit entangling chip. So I made this chip, and me and some other students work on measuring and designing this chip. And here's another very special device that someone else in our lab made. It has 4 qubits on it, and those 4 qubits were used all together to do a special quantum simulation of a kind of interaction that occurs in physics. So this is kind of a cool way that we can use qubits to simulate quantum physics. So these are just kind of examples of things that you can do in an academic lab. And that's all I've got today, but I'm happy to take plenty of time for questions and all the rest.
Wow, thank you so much, Sarah. That was an amazing presentation. We would now like to welcome questions from our Q&A section of the program from our online audience. Okay, so we're going to start off with a clarifying question. I know the word distribution was used very widely in the presentation, and I know that it's an important concept to understand in physics in general.
Yeah.
Can you clarify a bit, like what does it mean to be in a distribution of C positions or X positions, for example?
Yeah, so that's a great question. So basically, it's a question of being in a distribution versus just being in one place. So what we have to do is we have to measure something many times, and then kind of make a plot of all the things that we measured it to be. So let me think of a different place that distributions are used in the world. Well, distributions are used in, I suppose, I guess I would say maybe the weather. So you could basically sample the weather in different areas and then make a weather map of where all the weather is around you. So you can learn by making many measurements in different places in space, what is the weather like there? And then altogether you have a distribution. So the weather is not the same everywhere in space. So that's one example of a distribution in real life. And in quantum physics, everything works like a distribution, and that's because quantum measurements are different than classical measurements.
Okay, thank you so much for clarifying that. And now moving on to a little bit more of a abstract question. I know that quantum information science in general can feel a little bit more removed from our day-to-day life. Can you explain a little bit why the general public should be in the know about quantum information science, particularly quantum computing?
Yes. So basically, one of my good friends said a good quote to me once, which is that modern physics is on the nanoscale, basically. So things which you can't see with your eye, which are on chips, which are small. So like the chips that we talked about in today's presentation are basically this small. And then the features on them are much smaller. So basically, that's why everyone should know about this. Also, the chips in your cell phones are very small. And that is a related aspect of computing. So how are we going to learn about those things and things that govern those processes? So that's why qubits are interesting to everyone.
Thank you so much. Okay, one of our online audience member asks, this is a bit more of a career trajectory question, and I'll start off and I'll add on to this question a little bit just so that we can give a little bit more clarity. One, can you first explain what's the difference between a theorist and an experimentalist? And how did you decide that you wanted to be one or the other?
Yeah, so that's a good question. So I don't think there is a difference between a theorist and experimentalist except for what they choose to enjoy doing with their time more. So I guess that theorists and experimentalists both have big dreams for what they want to achieve, and their dreams might be exactly the same. So they're the same like that. But the experimentalist wants to make certain contributions, and the theorist wants to make other contributions. But one lovely thing about the field of quantum information science is that there is really not so much of a distinction between the two. Theorists, you could be an experimentalist one day and then a theorist the next, and the collaboration is very fruitful. That's because the field of quantum computing is in its infancy, and real quantum computers that really do things haven't been made yet. just little baby computers on the order of 100 qubits. It's going to be a lot bigger soon. So, in this infant phase, the theorists and the experimentalists are basically working very closely together because we need to bring the field out of its infancy. And how did I decide which one I wanted to be? Well, I guess I like working with my hands, so I'm more of an experimentalist.
Nice, thank you. Okay, this one is from one of our YouTube audience members. Why are the qubits in superposition?
Yeah, that's a good question. So the qubits are in superposition because um, we first of all we know that we made them. We know that they are qubits, and we made them so that they would be in their ground state. And then we pulsed them. We rotated them to the equator of the Bloch sphere, and now they're in a superposition all the way until they decay, which does happen shortly thereafter. So they are in superposition because we made them be in superposition. And one nice thing about these planar chips is that with a regular little pulse, kind of like a square pulse that you could make, you just can rotate them just like that.
Awesome, thank you. And on that note, I want to preface this question with a little bit of a piece of information that I recently learned. I recently learned that it's gene editing specifically is not very hard to do at home. And so a lot of folks do that, interestingly, especially like folks like dog breeders. And this question asks, hypothetically speaking, how do I build a quantum computer at home? So is it like gene editing? Can you do it at home in theory?
That's a great question. Whoever asked that question, kudos to you. So I think that, can you make one at home? Well, I guess that you can do some interesting things at home, but you can't fully make one and measure it at home because I forgot to mention something, which is that the qubit chips have to be cooled down to a temperature which is colder than outer space before their quantum information becomes visible to us. So that was a little detail which I overlooked. So unless you have a special fridge which can do that, you can't really measure one. But there are other things that you could do at home. One thing you can do at home is design qubit chips. There's a cool program called Qiskit Metal, which is online, and you can design cool designs and simulate classically how you expect those designs to perform. And then you can share your designs with others, and maybe those people have access to a fridge and they would simply love to make your design. So you can do the design process all the way from the bottom to the top, maybe with a little help from some friends which have access to a fridge. Um, but you can do that. And another thing you can do is you can kind of use a simulator to describe the behavior of qubits even without having one. So in the talk, I was using some graphics from a simulator called Quark, which I just found, which is on the internet. And you can actually get a lot of mileage out of Quark, and you can simulate 16 qubits. So whatever 16 qubits can do, you can simulate that spread of amplitudes. And you could maybe try to design an algorithm which is more efficient than anything anyone's ever come up with before. So those are some things you could try to do at home. One last thing, I believe IBM had like a prize of like $100,000 or something like that, maybe 50,000. I forget. Maybe 10,000 for for algorithm design, which anyone could apply to. So every year they have these prizes. That's just because no one knows. And only a few quantum algorithms have ever been made which have demonstrated a powerful advantage. But there are many more out there, and people are working on finding out what they are.
Hmm. Okay, so you just explained that we would need hypothetically a really intense or robust refrigerator,
Yeah.
right, to be able to cool the temp or cool the environment down. But what about, for example, the signals that are coming out of your computer, right? Like,
Yeah.
are they very small? And if so, what kind of devices do we need to be able to even read those signals?
Oh, so basically those pulses which I was talking about, those you could make from from a board at home. You could get a little board. There's a board which is called the Red Pitaya, which is kind of a nice board. It's maybe about $100, and you can program all those pulses yourself. And then you can send the signals out, and then you can loop them back in and kind of test. You could maybe even make pretend as to how a qubit would behave and make a little classical design as to how a qubit would behave so that you could use it to test your pulses on. So yeah, all of those signals are fair game to work with at home. The real problem is the fridge.
I see. Okay, thank you. And then going back a little bit, talking about states, right? So this question asks, since a classical bit takes either a 0 or a 1, how many values can a qubit take?
That's a great question. So actually, how many values can a qubit take? So yeah, that is a good question. So basically, a qubit technically can store two complex numbers inside it. Basically, its coordinate on the block sphere. And n qubits can store 2 to the n complex numbers. That amounts to that kind of spread of amplitudes that I was talking about. Whereas 64 classical bits can only approximate a real number. So basically, even with 64 classical bits, you store far less information than is in one qubit. So the problem with saying that is that when I say that, people immediately think that one qubit equals, two complex numbers free of charge, when really it's a little more subtle and it's about sampling a big space.
Mm,
But just to keep in mind, there is a lot of information stored in a qubit.
I see. And so is that then related to how this we hear a lot of like the speed advantage, right? Like is that then related to the speed advantage that quantum computers have over classical computers?
Yeah, so I would say that this sort of speed advantage comes from certain types of sampling problems, which would be in too large a space for a classical computer to sample well. So, this is something which I think is maybe a misconception about quantum computers is that they're like ultra fast at whatever that they do. It's more that they can represent a large space of possibilities with only just a few qubits. And because they can do that, um, you can kind of have access to that whole space by cleverly preparing and measuring the qubits. And it's a little bit subtle, but the advantages lie there. So maybe in the news there's been some results about how a classical computer could not sample a distribution as fast as the quantum one. But I think what really is more interesting is the strength of the quantum correlation and how quantum that correlation really is in the quantum computer than in the classical one. So basically, maybe they could be at the same speed, but the quantum computer can make a very big quantum correlation, and the classical computer could only ever try to like spoof that. So basically, fake that. So a real quantum correlation is something which a classical computer cannot do. And right now in today's big quantum computers like at Google or at USTC in China, those are where the biggest computers are. Um, right now, their quantum correlations are not very strong yet because there's lots of noise everywhere. So
Mm,
you can't really see all those quantum correlations, even though they are real qubits. So it's a matter of both making more qubits, but also just making them less noisy. Then they
thank,
can have really strong quantum correlations.
okay. Thank you so much for clarifying that. And another clarifying question from YouTube. Can you explain or re-explain and clarify down to the core, how would you explain how entanglement works?
Yeah, so entanglement is a quantum correlation between basically quantum objects. How does it work to the core? Is basically that it can be, so basically, if two quantum objects are entangled, they together are a pure quantum state together. To think of them separately would be incomplete, and it's only complete when you think about them together. When you measure one, you know about the other. They are correlated. And the origins of that correlation is something that we can engineer. It also arises naturally in nature, like with those experiments with the particles. So basically, we can make things that are completely connected, at least until they individually decohere.
Okay, thank you so much for clarifying all of that. I think it's always in physics. I think the clarifying questions are always the ones that are the
Yeah,
ones that stick.
I agree. And
Okay.
I'll just add that if you learn about the uncertainty principle, that is the rule of quantum mechanics, and that is equivalent to the idea of entanglement.
Thank you so much for adding to that. Now, transitioning a little bit more specifically to your work, can you explain a bit more on how your 2-qubit chip works?
Yeah, so these 2-qubit chips, well, they can be entangled, just like I was talking about, when we can engineer the entanglement. So we can send a special pulse, which entangles them. And then we see how good is that entanglement, and how reproducible is it, and how stable is our 2-qubit system anyway, and how coherent are our 2 qubits, and how cleanly can we read them out. And that's basically the point of the project. It would be thought of as a unit cell for something you could make a big chip out of. So what we do is we make new chips with new designs, and then we measure them, and we try various different types of entangling gates on them, because actually it turns out that there are different types, just like how NAND is only one gate, classical gate. There's also AND, OR, NOR, XOR, and everything else. There's lots of other gates in the quantum world too, entangling gates. And so we can try multiple types of gates and see which one's the best, and how many of them can we do. So that's what we do.
Awesome, thank you. And on the heels of that question, uh, this next question asked about what kind of careers exist in your field, but I think it would be really great if you could answer that question through how you plan to move forward after you defend and get your PhD.
Sure. So I'm a fifth year, so it's time for me to graduate. So once I graduate, I'm going to be a postdoc at Fermilab. And then I'm going to basically keep designing the qubits as much as I can. Basically, keep designing and redesigning them until they get better and better. And I'll try to do that with a couple qubits and maybe with even more qubits. So basically, it depends on what you like to do. And these things take years to develop skills for. So I just want people to know that the field is in its infancy. There's room for everybody if you like to work with your hands, if you like to do equations, if you like to do computer simulations, if you like to draw beautiful images of connected graphs, if you like to make clean a material or polish it or make a beautiful package out of copper, or if you like to measure things, like if you like to measure signals, or if you like to program computers, if you like to do any of those things, then this field is definitely for you. And I probably missed a lot of other things too. But yeah, it's basically you could become a grad student and a postdoc, or you could just kind of join a project which exists, which needs a research scientist or some kind of lab assistant, and then you could try to get your hands dirty working in a lab. So actually, I think help is needed in all areas. So it depends on whether you think you'd like to go to graduate school, or if you'd like to maybe work as a lab assistant in someone's lab for a while, or if you'd like to try to work at one of the companies like IBM. So there's a bunch of different ways to try to get involved in my type of quantum computing. So just shoot me an email if you ever have any questions about it.
Thank you so much. Um, so I know that you previously mentioned that there was an opportunity to talk about error correction, and this
Yeah.
question asks, perhaps you can touch upon this via this question, but they're asking how often do qubits go wrong?
Yeah, so qubits go wrong a lot. So basically, you can expect reliably that your qubit will go wrong on the time scale of its T1 time or its T2 time, which might be 100 microseconds. So that's very short. And then that's why we have to kind of control it and read it out very quickly. But, qubits' lifetimes are increasing as we engineer them better and better because we're learning how to control them and how to make them nice and stable. So over time, we're actually learning how to do this better, considerably better. Okay, so they go wrong a lot. But there is kind of another solution given to us by the theorists, even as we keep trying to design better qubits. That is called error correction. So basically, if quantum errors, which might occur from decoherence or from some kind of correlated noise, could happen on any of the qubits which are involved in an ongoing computing program, the rest of the computer could actually react in a special way such that the errors are corrected and the program can continue to run. So we don't have to start over. If an error happens, we can keep going. This theory is very well developed, and it's well known that if a prototype device can be engineered to have an error rate which is just below some threshold, then those qubits, which are still noisy, but they're kind of less noisy than some threshold, could be corrected into flawless qubits, which could reliably perform kind of sophisticated quantum algorithms. So that's what error correction is. And those two experiments, which I showed from ETH Zurich and from Google, were both little mini demonstrations of error correction. So that is very useful.
Okay, two questions about that. Could you briefly re-explain what decoherence is, and also, how do we know when the qubit goes wrong? How do we know the output is not what we expect to see or want to see?
Sure. So basically, after a period of time, the quantum state of a qubit or of a system of qubits decoheres. And that means that the coherent pure state, that quantum state along the Bloch sphere, for example, will collapse into an incoherent mixture of different states. After the state decoheres, it's going to contain no quantum information. And to keep using the system, we have to prepare the quantum state all over again. Each qubit is only as good as its coherence time, and a large qubit system is only as coherent as its least coherent qubit. So that's what decoherence is. Wait, I forgot the rest of it. Is that the question?
Oh, I think the other question was how do we know that the output is not correct?
Oh, that's a good question. So that's why we do kind of checking cycles. That's called error correction. So basically, during a checking cycle, we kind of use a helper qubit to check the state of one of our good qubits, and then we just know based on that, that like qubit on the right is always going to check the qubit on the left, and then we'll just use that qubit to know whether the one on the left had an error.
Okay, thank you so much for clarifying that.
Yeah.
I think we have time for one more question. And this is coming from YouTube, and it's a little bit of an involved question. But
That's fine.
they say, first of all, thank you. And they say, we use spin that provides us the space of all values of Bloch sphere. Why? Oh, never mind. This question is a little bit not coherent.
That's
um,
okay.
no worries.
Yeah.
We'll just move on to another one. There's
Okay.
plenty
Yeah.
of questions.
Oh, I'm glad that there's plenty of questions. That's good.
Yes, there, which is great. We have an engaged audience. Last question. How can you explain the attachment and entanglement, even though they don't have a physical connection? It almost feels as if it's connected by a field or gravity. Is
Yeah.
gravity quantum?
Yeah. So basically, gravity is a force which acts along long distances, but it's completely separate from entanglement. So basically, however, at the quantum scale, gravity should still exist. And basically, gravity's effects on the quantum scale are not yet well understood. And that's what's causing the great divide in physics between quantum mechanics and gravity. But you're correct that entanglement and gravity both act non-locally, meaning that, for example, the gravitational field at point A is affecting the field at point B, which is far away from each other. And that's also true for entangled qubits, which are far away from each other. So that is true about them. But the other rules which they work at have not been resolved consistently yet, and there isn't a coherent theory which unifies both of those yet. So I'm glad that people are asking questions about the nature of entanglement and why it is like that. And that's kind of what I wanted to bring up in this talk, because it is such a curious and interesting thing, which you can even make in the lab. And so if you've made it in the lab, don't you then understand its origins because you made it? And the answer is, to a level, yes. But to a level, it is still mysterious to us. So basically, I guess the thing is that you can, it's like you can do things in the quantum world and gain an intuition for them, but not understand their origins. So the best origin is the uncertainty principle that I know of, but maybe you'll join the field and learn a better origin.
Thank you so much, Sarah, and thank you so much, everyone, for your great questions. A professor once told me that the least someone knows about something, the better fundamental questions they ask. And so I think that's why these types of programs are so important. Thank you again, Sarah, for sharing your insight and knowledge in a way such that we could learn about quantum computing in such an accessible and simple manner. Just some announcements. Catch C2ST at the Museum of Science and Industry's Women in STEM Showcase this Saturday, March 27th, from 9:30 a.m. to 2:30 p.m. And if you're interested in joining us as a volunteer, please contact me, D. Hernandez, at c2st.org. We also have a slew of upcoming programming. On March 28th at 5:30, we will be at Wabanzi Community College discussing the experience of Latina professionals in the tech space. On April 5th at 5:30, C2ST will be partnering with IIT to deliver a program on energy transitions. If you like today's program, consider joining the rest of our QIS program series. We will be discussing all things quantum communications and sensing on May 25th and June 1st, respectively. Both programs will be held from 7 to 8 p.m. Evaluate today's session at c2st.cnf.io and be entered to win a gift card. To support more programs like this one, please donate at c2st.org and consider giving $15 in celebration of our 15th year. And sign up for a weekly C2ST newsletter to stay up to date on what's happening in STEM. Thank you so much again for sticking around to tonight's program. We really hope you learned something new. And now comes the most important part. If you enjoyed what you just watched, please consider subscribing and liking this video. And if you really liked the video, please leave a comment. Thanks so much for watching, and thank you so much for joining us tonight. And thank you again, Sarah.
Thank you.